Good day. The topic we are treating today is geometric progression by Opola Monsurat Olajimoke. Before the commencement of this topic, you must have been familiar with what a sequence is, the rules of indices, roots of numbers, quadratic equation and method for solving them, equation of powers, simultaneous equation and methods for solving them, especially the substitution method, and so on, so that by the end of this lesson, you will be able to solve different questions on geometric progression. The geometric progression. The geometric progression, also known as the exponential sequence, is a sequence in which any two consecutive terms differ by a constant multiple or factor. In a geometric progression, each member is called a term. The constant multiple or factor is called the common ratio, and it is denoted by R, and it is given by the formula is that you divide the second term by the first, or you divide the third term by the second term, or which is the same thing as dividing the nth term by the n minus 1 term, while the first term is represented by A. Examples of geometric progressions with their first term and common ratios are: the first one is 6, 8, 6, 18, 54, 162, and so on. Here the first term is 6, that is the first number in the sequence. So to get the common ratio following the formula given above, it's either you use the second term, you divide the second term by the first, which is 18 divided by 6, you have 3, which must be equal to dividing the third term by the seconds, which is equal to dividing the third term by the second term, which is 54 divided by 18 to give 3, which is also equal to dividing the first term by the third term, whereas 62 divided by 54 to also have 3. Therefore, we have the common ratio R to be equal to 3. So move to the second example: 16, 24, 36, 54, 81, and so on. Here the first term A is 16, that is the first number in the sequence. So to get the common ratio, it's either we divide the second term 24 by the first term 16 to get 1.5, or you divide the third term 36 by the second term 24 to get 1.5, or you divide the first term 54 by the third term 36 to get 1.5, and so on. Since it has a unique ratio 1.5, therefore this particular sequence is a geometric progression with first term A to be equal to 16 and common ratio to be equal to 1.5. So we'll move to the third example: 20, minus 10, 5, minus 2.5, 1 whole number 1/4, and so on. Here, the first term is 20, that is the first number in the sequence. So to get the common ratio, is either you divide the second term minus 10 by 20 to get minus half, or you divide 5 by minus 10, or you divide minus 2.5 by 5, and so on. So here we have a unique common ratio which is minus half. Therefore, this particular sequence is a geometric progression with first term A to be equal to 20 and the common ratio equals to minus half. The nth term of a geometric progression. If the first term T1, which is denoted by A, and the common ratio denoted by R is known, then the process of finding the second term, that is the second term of a geometric progression denoted as T2, is by multiplying the first term A by the common ratio R to give AR. Also, to get the third term T3, the second term, which is AR, is multiplied by the common ratio R. AR multiplied by R will give AR squared. So to get the fourth term, we multiply the third term AR squared by the common ratio R to get AR cubed, and so on. Therefore, the general form of a geometric progression will be of the form A, AR, AR squared, AR cubed, AR raised to power 4, and so on. So if you observe this critically, it is noted that the number of times the common ratio must be multiplied to the first term in order to get the next term is one less than the term being sought. What we are trying to say here is that already we have A to be the first term. So when I want to get the second term T2, this is the second term, the term number 2. We observe that we only multiply the common ratio once with the first term, that is 2 minus 1 multiply. That is why they say 1 less than the term being sought, 1 less, that is 2 minus 1 we give 1, we multiply by a single common ratio. So to get the third term, you are in the term number 3. 3 minus 1 is 2, so you multiply the common ratio twice with the first term to get the general form of the third term. And same thing is applicable to all other terms in the geometric progression. And also the nth term is denoted as t subscript n. Therefore, the nth term of a geometric progression, that is, if you are very familiar with the sequence, you know the nth term is like generalization of that particular progression, so that if you substitute any value of n to this place, you get the terms in the sequence. So here c subscript n is given as a, which is the a you usually multiply with, and r, you know they said the term you are looking for. To get that term, you must multiply r in n minus 1 time, that is 1 less than the term being sought. Here we are dealing with the nth term. The term being sought here is term n, so it must be 1 less than r. That is why we have r raised to power n minus 1. So the nth term of the geometric progression is equal to a multiplied by r raised to power n minus 1. So to check if this general term is correct, let's check for T3, that is the third term. You know here the third term is ar squared. Let's see if we are going to get ar squared here also. So n is 3, T3 is equal to a raised to power 3 minus 1. 3 minus 1 is 2, and we also have a squared. Also, let's check the fifth term, that is when n is equal to 5. T5 equals to a raised to power 5 minus 1, which is a raised to power 4, which is what we have here. So this particular nth term will generate all the terms of a geometric progression. So this is the general formula for generating the terms of a geometric progression. The above is therefore the general formula for finding an unknown term of a geometric progression. You can find the 50th term without multiplying the preceding term by r. You can find the 50th term straight from this place. So now we move to examples. Here we have 4 examples. One is from the UTME past question, UTME 1993. So we now move to the solutions of these examples. The first example, we are told that the second term of a geometric progression is 8/9 and the sixth term is 4.5. We are asked to find the first term a and the common ratio r. We all know the formula for the nth term of the geometric progression to be t subscript n equals to a r raised to power n minus 1. Since the value for the second term, which is denoted as t2, is given as 8/9, from the formula of this nth term of the geometric progression, t2 equals a r raised to power 2 minus 1, which is a r. And the value for T2 is already given as 8/9. This implies that 8/9 is equals to AR, and that is tagged as the first equation. Also, the sixth term, the value for the sixth term, that is the value for T6 is 4.5. That is from the formula of nth term of the geometric progression, T6 is equals to a raised to power 6 minus 1, which is a raised to power 5, and the value for T6 is given as 4.5, which implies that 4.5 equals a raised to power 5, and that is tagged as the second equation. So to get the value for either a or r, we divide the second equation by the first. So if you divide the second equation by the first, you know here 4.5 can be written as 9/2 when converted to improper fraction. So 9/2 we divide 8/9, which is equals to a r raised to power 5 divided by a r. Here we cancel a. 9/2 divided by 8/9 is same thing as writing 9/2 multiplied by 9/8, which is 81/16. And according to the rule of indices, a raised to power m divided by a raised to power n is equals to a raised to power m minus n. That is why we have r raised to power 5 divided by r raised to power 1 equals to r raised to power 5 minus 1, which is what we have here. So 81/16 is r raised to power 4 because 5 minus 1 equals 4. So in order to, here we are looking for the value of the common ratio alone, not the common ratio raised to the power of 4. So in order to eradicate this fourth power, we have to introduce fourth root. We have to take the fourth root of both sides, because whatever you do to the right hand side, you must also do it to the left hand side. That is, the fourth root of 81/16 equals to fourth root of r raised to power 4. So if you are taking the nth root of a particular number, that is the nth root of a particular number is the same thing as that number raised to power 1/n. So taking the fourth root of this number means 81/16 raised to power 1/4, and taking the fourth root of r raised to power 4 is also equals to r raised to power 4 raised to power 1/4. And we also know that 81 can be written in exponential form as 3 raised to the power 4. That is, if you multiply 3 4 times, you get 81. And 16 can be written as 2 raised to the power 4. Everything raised to the power 1 over 4. And we have this back. So also, if you have a over b raised to the power n, this can be written as a raised to the power n divided by b raised to the power n. So this can be written as 3 raised to the power 4, everything raised to the power 1 over 4, divided by 2 raised to the power 4, everything raised to the power 1 over 4. And we also have this. So following the rules of indices, a raised to the power n, everything raised to the power 1 over n is equals to a, because it's like saying a raised to the power n multiplied by 1 over n here 1, n here 1, a raised to the power 1 will give a. So we apply this rule into this. 3 raised to the power 4 multiplied by 1 over 4 raised to the power 1 over 4 is 4 here 1, 4 here 1, 3 raised to the power 1, we get 3, 4 here 1, 4 here 1, 2 raised to the power 1, we get 2, 4 here 1, 4 here 1, r raised to the power 1 will get r. Therefore, the value for r is 3 over 2. Now, we substitute the value for r equals 3 over 2 into any of the equations, that is, either equation 1 or 2. So here we choose to substitute the value of r into equation 1 to obtain the first term, and the statement for equation 1 is 8 over 9 equals to ar. We know the value for r is 3 over 2. We substitute. It implies that 8 over 9 is equals to a multiplied by 3 over 2. So here, we want to make a the solid of formula. We have to multiply both sides by the reciprocal of 3 over 2, which is 2 over 3. So we multiply this side by 2 over 3. We have 8 over 9 multiplied by 2 over 3. And multiply this side by 2 over 3. 3 over 2 multiplied by 2 over 3 will give 1. 1 multiplied by a will give a. And we are left with a equals to a over 9. 8 over 9 multiplied by 2 over 3. 8 multiplied by 2 will give 16, and 9 multiplied by 3 will give 27. Therefore, the first term here is 16 over 27, and the common ratio is 3 over 2. And that solves the first question. The second question says, if k plus 1, 2k minus 1, 3k plus 1 are 3 consecutive terms of a geometric progression, then we should find the possible values of the common ratio. Here, these are 3 consecutive terms, that is 3 terms that follow each other consecutively, and they are terms of a geometric progression. So we want to find the possible values of the common ratio of that geometric progression. And from here, we don't know the term they are. It can be the first, second, third term. It can be the fifth, sixth, seventh term. So let's call this the n minus 1 term, the nth term, and the n plus 1 term. So here, we know from the idea of geometric progression that if you want to find the common ratio of geometric progression, is either you divide this term by this term, which is equal to dividing this term by this term. That is, 2k minus 1 divided by k plus 1 is equal to 3k plus 1 divided by 2k minus 1, and that gives the common ratio. So we'll pick these two. 2k minus 1 over k plus 1 equals 3k plus 1 over 2k minus 1. So we cross multiply. 2k minus 1 will multiply 2k minus 1, which is equal to 3k plus 1 multiplying k plus 1. So here, we expand the brackets. We have 4k squared minus 4k plus 1 equals 3k squared plus 4k plus 1. So we collect the like terms, we move everything in the right hand side to the left. We are left with 4k squared minus 4k plus 1 minus 3k squared minus 4k minus 1 equals 0. So collect the like terms, 4k squared minus 3k squared minus into 4k plus 4k plus 1 minus 1 equals 0. So here 1 minus 1 will be 0. 4k squared minus 3k squared is k squared. Minus into 4k plus 4k will give minus 8k equals 0. So if you are very familiar with quadratic equation, you know that we have to factorize out k because k is common to both sides. So factorize k out, k into k minus 8 equals 0. Also, if you're also familiar with the solutions of the quadratic equation, you know it's either k equals 0 or k equals 8. So we have two values for k. So substitute both values of k into the terms of that geometric progression and look for the possible values of r. Since we have two values of k, we already know we are going to have two values of r. Substituting the value k equals 0 into the consecutive terms, the first one is k plus 1, which is 0 plus 1, we give 1. The second one is 2k minus 1, that is 2 multiplied by 0, 0, 0 minus 1, we give minus 1. And third one is 3k plus 1, 3 multiplied by 0 is 0, 0 plus 1, we give 1. So here, to find the common ratio of this particular geometric progression using these three terms, the common ratio will be minus 1, that is the second the middle term divided by the first, which is equals to the last divided by the middle, which will all give -1. That is, when k is equal to 0, the value for the common ratio r is -1. Also, we substitute the second value of k, which is 8, into the consecutive term. So we have the sequence. The first one is k plus 1. 8 plus 1 will give 9. The second one is 2k minus 1. 2 multiplied by 8, 16 minus 1 will give 15. The third one is 3k plus 1, which is 3 multiplied by 8, 24 plus 1 will give 25. Also, we find the common ratio here, which is either 15 over 9, which must be equals to 25 over 15. So here, 3 here 5, 3 here 3, also 5 here 5, 5 here 3, this is 5 over 3. That is, when k is equals to 8, the value of r is 5 over 3. Therefore, the particle values of r is -1, 5 over 3. And that answers the question. Now we move to the third example. Here, we are given the first term of that particular geometric progression to be half. And the value for the term we are to look for, that is the last term, is given as 3 raised to the power 9 over 2 raised to the power 10. But we don't know that particular term. We don't know the term we are in, but we know the value of that term is 3 raised to the power 9 over 2 raised to the power 10. And the sequence is 1 over 2, 3 over 4, 9 over 8, and so on. So we can find the common ratio using this, which is either dividing 3 over 4 by 1 over 2, which is equal to dividing 9 over 8 by 3 over 4. And if this is evaluated, we have the common ratio to be 3 over 2. So here, the value for the first term is given as half. The value for the common ratio is 3 over 2. The last term, that is, it is a finite geometric progression, is 3 raised to the power 9 over 2 raised to the power 7, but we don't know that particular term. So that is what we have to obtain. So from the formula of the nth term of the geometric progression tagged as b here, we know that Tn is 3 raised to the power 9 divided by 2 raised to the power 10, which is equals to a, which is half, and the common ratio is 3 over 2 raised to the power n minus 1. So if we first eradicate this half by multiplying both sides by 2, we have 3 raised to the power 9 multiplied by 2 over 2 raised to the power 10 equals to 2 here 1, 2 here 1, you have 1 multiplied by this, you are left with 3 over 2 raised to the power n minus 1. So here we have 3 raised to the power 9 multiplied by 2 over 2 raised to the power 10. According to rule of indices that we talked about earlier, a raised to the power m divided by a raised to the power m is equals to a raised to the power m minus n. So 2 raised to the power 1 divided by 2 raised to the power 10 is the same thing as 2 raised to the power 1 minus 10, which is equals to 2 raised to the power minus 9. And also, according to rule of indices, 2 raised to the power minus 9 can be written as 1 over 2 raised to the power 9. And that is why we have 2 raised to the power 9, 3 raised to the power 9 over 2 raised to the power 9 equals to 3 over 2 raised to the power n minus 1. So here we take this back to its original form. We said according to the rule of indices, a raised to the power m over a raised to the power n is a raised to the power n minus 1. So 3 raised to the power 2, 3 over 2 raised to the power n minus 1 can be written as 3 over 2 raised to the power n divided by 3 over 2 raised to the power 1. So that if you bring it back to this form, we have 3 over 2 raised to the power n minus 1. So we'll take it back to the original form and we have this. So here, we also multiply both sides by 3 over 2. This is the denominator. We multiply both sides by 3 over 2. So we have 3 over 2 here 1, 3 over 2 here 1. We are left with 3 over 2 raised to the power n. So if you multiply this side by 3 over 2, according to the rule of indices, a raised to the power m multiplied by a raised to the power n is equals to a raised to the power n plus n. So 3 raised to the power 9 multiplied by 3 raised to the power 1 is 3 raised to the power 9 plus 1, which will give 3 raised to the power 10. 2 raised to the power 9 multiplied by 2 raised to the power 1 is 2 raised to the power 9 plus 1, which will give 2 raised to the power 10, which will be equals to 3 over 2 raised to the power n. Also, we know that a over b raised to the power n is the same thing as writing a raised to the power n over b raised to the power n. That is why we have 3 over 2 raised to the power n equals to 3 raised to the power n over 2 raised to the power n. So now if we equate powers, we have 3, 3, 2, 2, and n is the same. Therefore, n is 10. That is, for that particular geometric progression, it is the 10th term that gives us 3 raised to the power 9 over 2 raised to the power 10. If we should substitute n to be equal to 10, a equals to half, and r equals 3 over 2, we get back 3 raised to the power 9 over 2 raised to the power 10. And that solves the question. So now we'll move to the fourth question. The first question says the sum of the first and third term of a geometric progression is 7/3 and the sum of the second and fourth term is 7/4. It has to find the first term and the common ratio. So here the nth term of a geometric progression is Tn equals a raised by n minus 1, and that is that is this equation C. So from C, the first term, which is T1, is A. That is 1 minus 1 is 0, r raised by 0 is 1, a multiplied by 1 is a. The second term, T2, is a r raised by 2 minus 1, which is a r. The third term from here is a r squared. The fourth term is a r cubed. So here we move to the question. In the question, it is said that the sum of the first term, which is T1, and the third term, T3, is 7/3. The value for T1 is a, plus the value for T3 is a r squared equals 7/3. That's from the question, and that is tagged at equation D. Also, it is given that the sum of the second term, here it is a r, plus the fourth term, a r cubed, is 7/4. So from here, D and E gives us a simultaneous equation. So we have to solve this using the substitution method. So from D, we can factorize A out. We have here A into 1 plus r squared equals 7/3. So to make A solve the formula, we divide both sides by 1 plus r squared, which is the coefficient of A. Therefore, A will now be equal to 7/3 multiplied by 1 plus r squared. So we now substitute the value of A that we got from D into E. So we have, that one is a r. So A here is 7/3 into 1 plus r squared multiplied by r, plus 7/3 into 1 plus r squared multiplied by r cubed equals 7/4. 7r, 3 into 1 plus r squared, 7r cubed, 3 into 1 plus r squared equals 7/4. So we take this to this side, changes to minus 7/4. We first find the LCM here. We have the same denominator, 3 into 1 plus r squared, so it can be written as 3 into 1 plus r squared in 3 into 1 plus r squared, which is 1 multiplied by 7r plus, which is this positive sign, 3 into 1 plus r squared in 3 into 1 plus r squared, which is 1 multiplied by 7r cubed is 7r cubed. So we take this to this side, we have minus 7/4 equals 0. Also, we combine the fractions by taking the LCM. Here the LCM is 4 into, this is 3 multiplied by 1, 3 multiplied by r squared, 3r squared. That is how we got this. So here 3 into 1 plus r squared, here we have 4 remaining. So 4 will multiply the numerator minus 4. 4 will divide 4 here, we are left with 3 plus 3r squared. We divide it by the numerator 7, which is equal to 0. So now we multiply through by the denominator. We multiply this side by the denominator, we have 1. This we cancel this, we are left with the numerator. And to eradicate this, we multiply both sides by 4 into 3 plus 3r squared. So if we should multiply this side by 4 into 3 plus 3r squared, that we cancel that, we have 1. And if we multiply 0 by 4 into 3 plus 3r squared, we have 0. So we are left with only the numerator here. So we expand the bracket. 4 multiplied by 7r will give 28r. 4 multiplied by 7r cubed will give positive 28r cubed. Minus 7 multiplied by 3 will give minus 21. Minus 7 multiplied by 3r squared will give minus 21r squared equals 0. So now we rearrange from the highest power of r. So the highest power here is the cube, which is 28r cubed. Then the square power minus 21r squared plus 28r minus 21. Here we can see that all these are multiples of 7. So we can divide through by 7. So if we divide this piece by 7, we have 4r cubed minus 3r squared plus 4r minus 3. And if you divide 0 by 7, we also have 0. We can also rearrange. This can be written as 4r cubed plus 4r minus 3r squared minus 3. So we factorize. This can be written as 4r because 4r is common to both, 4r into r squared plus 1, because if we should expand the bracket, we get this back. We can factorize out minus 3 into r squared plus 1, which is equal equals to 0. If you are very familiar with quadratic equation, you know that this can be written as 4r minus 3 multiplied by r squared plus 1, because if you should expand this bracket, we get the equation back, which is equal to 0. So here is either 4r minus 3 equals 0 or r squared plus 1 equals 0. If 4r minus 3 equals 0, then r will be equals 3 over 4. And if r squared plus 1 equals 0, that is r will be equals to plus or minus I, which is a complex constant. Since r cannot be a complex number, then r will be equals to 3 over 4. So to get the first term, we substitute the value for r equals 3 over 4 into d, that is the term where we make a sort of formula, and the statement for equation d is a plus ar squared equals 7 over 3. So we substitute the value of r 3 over 4, which is a plus a 3 over 4 squared equals 7 over 3. And you know 3 squared is 9, 4 squared is 16. That is why we have a plus 9 multiplied by a will give 9a, 4 squared 16 equals 7 over 3. So here we find the LCM. LCM is 16, 1 is 16, 16 multiplied by a will give 16a, plus 16 is 16, 1 multiplied by 9a will give 9a, 16a plus 9a is 25a, equals to 16 equals 7 over 3. So to make a sort of formula, we divide through by 25 over 16. So if you divide by 25 over 16, 25 over 16 here, 1, 25 over 16 here, half, we are left with a. So this will now be 7 over 3 divided by 25 over 16, which is something as 7 over 3 times 16 over 25. So 7 multiplied by 16 will give 112, and 3 multiplied by 25 will give 75. Therefore, the first term is 112 over 75. So we now have the value for the common ratio at the first term. So if we should multiply the first term here, if we should add the first term a to the third term, ar squared, you will see that the answer will be equal to 7 over 3. And also if you add the second term ar to the fourth term, ar cubed, the answer will be 7 over 4. You can check this. So these are exercises to see if you really understood what we have been explaining. We have some from the UTME past questions with UTME 2003. So next video will be on properties of geometric progression. Please subscribe to our YouTube channel, like and share our videos. Thank you.